lecture is on the Sylow theorems. But in the proof of one of the pieces of the Sylow theorems, I want to use Cauchy's theorem. And at this point, we've proven Cauchy's theorem for finite abelian groups. We did that several lectures ago. That's proposition 21 in section 3.4. But we haven't proven the full statement of Cauchy's theorem. So before getting to the Sylow theorems, I want to state and prove Cauchy's theorem. So before doing the proof in general, let's review how the proof worked for finite abelian groups. And the main idea was to do induction on the size of the group. We just take some non-identity element of G. If P divides the order of that element, then we can take a power of this element whose order is divisible by P to actually find an element of order P. So that case is OK. The other case is more interesting. So we suppose now that P doesn't divide the order of this element X. And we consider the quotient of G by the normal subgroup generated by X. This is a cyclic subgroup generated by X. It's automatically normal because G is abelian. So this is a main idea, is that this group has order smaller than the order of G. So our induction hypothesis was that we're going to assume that Cauchy's theorem holds for all groups of size less than G. And this is one of them. So P still divides the order of this group. So by induction, there's an element y bar of order P in this quotient. And this element y bar gives us an element y in G. And what we know about y is that y is not in the cyclic subgroup generated by X, but y to the P is in the cyclic subgroup generated by X. You can use this to show that P divides the order of y. And now we're back in this case where P divides the order of some element. So from y, we take a power of y, and we get an element of order P. OK, so that's how the proof worked in the finite abelian case. Now let's see the general case. So Cauchy's theorem says G is a finite group, and P is a prime dividing the order of that group. Then G contains an element of order P. And the idea for the general case will be similar. We'll do induction on the size of G. So now I'll be a little more careful and precise about how that works. Let's say that the order of G is n, and P is a prime dividing n. The base case of this induction will be n equals P. So that's certainly a positive integer where P divides it. And Cauchy's theorem for n equals P is trivial. We already know that every group of order P is cyclic, and every non-identity element has order exactly P. So Cauchy's theorem definitely holds in this base case. So we're going to suppose that n is bigger than P, and P divides n. So now we're supposing that Cauchy's theorem is true for all groups of order m less than n, where P divides m. The argument splits into two cases. The abelian case we have already done. So the rest of the proof, we're going to suppose that G is a non-abelian group of order n, and that no element of G has order P. And our goal now is to get a contradiction. So I'm going to pause and erase, and then give you the rest of the proof. Let's finish this proof. So we've supposed that G is a non-abelian group of order n, and no element of G has order P. And the big idea is to argue by induction on the size of G. So what does induction get us? Let's say that H is a proper subgroup of G. Certainly, H has no element of order P, because if H had an element of order P, so would G. So what does that mean? H is a group whose size is smaller than n, the size of G. So if P divided the order of H, that would mean that H would have to have an element of order P by induction. So what induction tells us is that no proper subgroup H of G has order divisible by P. So what does that mean? If P doesn't divide the order of H, because for every proper subgroup H, we have the size of G is equal to the size of H times the index of H in G, P divides the left-hand side. So if P doesn't divide this first term, it has to divide the index of H and G. Okay, so that's the first really big idea that goes into this argument, is showing that P has to divide the index of any proper subgroup. And that very much uses the induction hypothesis. All right, the second big idea is to use the class equation. So since G is a non-abelian group, it has some conjugacy classes of size bigger than 1. Right? What does it mean for a group to be abelian? It means the center is the whole group. The elements of the center are exactly the orbits of size 1 under the conjugation action. So let's let G1 up through Gk be representatives of these conjugacy classes of size bigger than 1. So what does the class equation say? It says the size of G is equal to the size of the center, the number of fixed points, plus the sum of the sizes of the other orbits, which by the orbit stabilizer theorem, each orbit is the index of the centralizer of some representative inside the whole group. And now, since each conjugacy class has size bigger than 1 over here, the conjugacy class of Gi has size bigger than 1. That means that the centralizer of Gi is not the whole group G. So what does that mean about the centralizer? It is a proper subgroup of G. And by induction, every proper subgroup, P divides the index. So that means P divides the index of the centralizer of Gi inside G for every I. So now look at this equation. P divides the order of the group, G. P divides every term in this sum. So that means P divides the order of the center. But that's a problem, because by induction, no proper subgroup H of G has order divisible by P. And now we've just shown that P divides the order of the center. And the center is a subgroup. So what does that mean? The center isn't a proper subgroup. So the center of G is equal to G. And that means G is abelian. But we already proved this theorem in the case that G is abelian. So that is the end of the proof. OK, so a little while from now, when you think to yourself, how does the proof of Cauchy's theorem go? The way that I remember it is you prove Cauchy's theorem for finite abelian groups by induction on the size of the group. There are two cases. You take some element and you either think about when P divides the order of the element, things are pretty easy. When P doesn't divide the order of the element, take the quotient of your group by the cyclic subgroup generated by your element. OK, so what about the general case? Same idea, induction on the size of the group. You already know the case when G is abelian. So the only case left is G is non-abelian and it has no element of order P. And then the big idea is, what does induction tell you? Induction says no proper subgroup has order divisible by P, which means that P divides the index of every proper subgroup. What do you do with that? You do the class equation and look at what it tells you about each term in the class equation mod P. So in the next video, I'll state the Sylow theorems. And when we're proving the first statement of the Sylow theorem, part of why I did this argument now was that one of the proofs that I'll give for this first big part of the Sylow theorems, the argument very much follows this style.